Exponential models. 1. Massachusetts had a population of 6 million and change in 1990 and 6.3 million in 2000. Assume growth is exponential. A. Find a formula for the population t years after 1990. So we'll start with our general exponential formula. P of t is a times b to the t. We know that a is the starting amount, and this is years since 1990, and fortunately we're given exactly what's happening in 1990. So that means that the a value is this number right here, the 6 million and a little bit more. This is a, so that's kind of nice. And then in order to plug in the other point, we just have to know how many years it's been since 1990. So the year 2000 is 10 years from 1990, so 10 is the value of t that we're going to plug in. So let's plug in this blue equation. I'll start with the right-hand side. A, we just found, it's given to us, is this 6 million and change, times b, which we don't know, raised to the t power. T is 10 in the year 2000. And the left-hand side is the population in the year 2000, which is that 6.3 million and change. Okay, and all we need to do here is solve for b. So let's divide both sides by the 6,016,000 number. So I'm just going to do this over here. That's equal to b to the 10th. And then solving for b, take the 10th root of both sides. I'm going to be lazy because I don't want to write all these numbers again. And I'll just put 10th root over here. Technically should put a plus or minus in, but we know b is always positive. So that's the value of b. Let's get an estimate on the calculator. So first we type in the 10, then we go second math. Nope, then we go just math, and it's there, number 5. And then parentheses as we type this long number out. So we get about 1.0054. I'm going to write down 1.0054, but I'm going to store this as the number b, just in case we want to use it later. That will be the most accurate way to use that answer. So b is roughly 1.0054. And then our formula is therefore p of t equals, so it's the 6 million and change number times this 1.0054 raised to the t. That's our formula. Part B, what's the percent growth rate? So there's a nifty little formula that tells us the percent growth rate related to B. It's just B equals 1 plus R, where R is this percent growth rate that we're asked to find. So let's just go ahead and write in, instead of B, it's this 1.0054. That's one more than R, so just subtract 1 from that number, and we get R is about 0.0054. So about 0.54%. So about 0.5%. Part C, what's the estimated population for 2009? So again, we need to figure out what the value of t is in 2009. So we saw up here that 1990 is the starting value. So in 2009, how many years later is that? That's 19 years later. So in this part, we know that t equals 19. So this is really just asking us to find p of 19. And our formula for p is right there in blue, 6 million and change times 1.0054 raised to the 19th power. And instead of typing that in as it is, well, maybe we'll type it in as it is, and then we'll type it in the better way. So that's multiplied by 1.0054 raised to the 19th power. So that's the answer, which is rounded, because this 1.0054 was rounded. So maybe better, I'll do second entry to get this back up here. I'm going to delete all this gobbledygook, and we're just going to put B, think we stored this as B. And so that's the most accurate answer that we can get. And you can see the difference. We're off by 448 people. That's kind of a lot. And that was only after 19 years. So much better to get the best answer your calculator can give. So we'll write in our number here. We've got 6,664,000, about 201 at the end. And I'd encourage you to take advantage of that store button on the left-hand side there at the bottom, storing numbers so that you don't have to write down a lot of digits. Okay, number 2. The atmospheric pressure is 1,013 millibars at sea level, and it decreases by 14% for every 1 kilometer increase in altitude. Part A, find a formula for the pressure at an altitude x. Okay, so I guess we're still doing this percent, the exponential growth function. So it used to be a times b to the t. I still like using p for pressure, but they're saying x is the altitude. So how about we change it to a times b to the x? This is now pressure as a function of x. Okay, that 1,013 millibars is at sea level. That's when x is 0, and that's the a value. That's the initial value. A is 1,013. So far, so good. P of x is now 1,013 times b to the x. Got to find b. Well, in this case, we don't have to do a lot of work. We just have to analyze. It says that the pressure decreases by 14% for every 1 kilometer increase in altitude. 14% per every unit. So we know that b is 1 plus r, and the r that is given in this problem is negative 0.14. Decrease, that's the negative, and then 14% change it to a decimal is 0.14. So the b is simply 0.86. So our formula, our completed formula, is 1,013 times 0.86 to the x. Part B, what's the pressure at 10 kilometers and at 50 kilometers? So we just have to plug in 10 for x and then 50 for x. 1,013 times 0.86 to the 10. And we'll get a decimal there, and then same thing but with a 50. Okay, so let's type each of these things in. Okay, so about 224 and change, that many millibars was the first answer, and then second enter, we'll make it so I don't have to retype everything, but just change the 1 into a 5. Ooh, big difference. So about 224.2, and then 0.5 is the second answer. Part C, what is the horizontal asymptote and what does it signify in this case? Use limit notation. Okay, well, we know that this is an exponential function, and we know that since the b value is 0.86 and it's smaller than 1, this is exponential decay, which makes sense because the pressure is decreasing. That was given in the problem. And when you have exponential decay, what does the graph go to as you run to the right forever? Well, it gets closer and closer to the horizontal axis, the x-axis. So, so I guess we'll say that the pressure tends to 0 as the altitude increases. The higher and higher you go in altitude, the lower and lower the pressure, tending to 0. Never technically hitting there, but getting very, very close. And you can see that. It's 1,013 at sea level, and then you go 10 kilometers up, and you're down all the way to 224, and 50 kilometers, and you're only at half a millibar of pressure. Half a millibar compared to 1,000 millibars. So if we want to use limit notation, this is good practice. limit as x goes to infinity of the function. The function, the rule is p of x in this case, and that is equal to 0. Part D, at what altitude is the pressure 800 millibars? Solve this one on the calculator today. We'll solve it algebraically using logs in a couple of classes. So let's write our formula right there at the top right of the screen in blue. That's where we start. And we're trying to make it so that the pressure is 800, so we put 800 over here. And we solve for x. So first we'll move the 1,000 over to the other side by dividing. And then if you know something about logarithms, you might be able to use them to solve for x algebraically. If you do, then certainly you can do it that way. That's good practice. We'll be doing it that way together soon. But for right now, I think all we can do is graph both sides of this equation and intersect. So we'll go into y equals. I'm going to type in 800 divided by 1,013. And then in the other one, it's a 0.86 raised to the x. And instead of doing zoom 6, I mean, you can do zoom 6, but it's just a bad idea. No, well, maybe it's not such a bad idea. It's possible that the intersection happens here. I can't tell what's going on because things are so small, but maybe it happens there. Let's go back and look at the numbers we have and see if we could estimate the answer. We start at 1,000 millibars, and then if you go 10 kilometers up, you're down to 224. Okay, so then if we wanted to get to 800, since 800 is between the 1,000 and the 220, then the answer's got to be between sea level 0 and 10. Okay, the answer is somewhere on this window. Even though we can't see it, calculator can see it no problem. So second intersect and then enter 3 times. And it'll get us the answer even though we can't see it specifically. So that's the answer right there, 1.565. But I don't really like not being able to see what's going on. So I would much prefer to say, okay, I know the answer is going to happen somewhere between sea level 0 and 10. And then as far as the window goes, well, all I need to do is make sure that I can see the graph of this thing right here. And 800 divided by 1,013 is roughly 0.8. So I'm just going to look between 0 and 1. That will really zoom me in on the part that's important. 0 up to 1. So there's 0.8, 8/10 of the way up, and then we'll see our exponential decay. And I'd much prefer intersecting here, much more comfortable because I can see exactly what's going on. This is 10, so it sure looks like the answer is something between 1 and 2. So now we'll do second calc, and then number 5, enter, enter, enter. And we'll get the same 1.565 as we got before, but this is more satisfying, at least in my opinion. So from the calculator, we see that x is roughly 1.565. So that's how many kilometers you should be up at if you want the pressure to be 800 millibars. Now the fact is we probably didn't even need to divide by the 1,000. We could have graphed both sides of this equation. So let's do that quickly. So the first equation just becomes 800. And the second equation becomes 1,013 times 0.86 to the x. Now the window that we have here is just no good anymore. So in this case, we need to be able to see the pressure up there at 800. We need to see a horizontal line at 800. So how about we make the y max 1,000? And then maybe hash marks every 100. So the picture looks pretty similar to how it looked before. There's just been a massive scale change here, but I think you can save yourself some aggravation and some trial and error if you really think carefully about what the window should be instead of just kind of trial and error as you find a good window.